Recording in progress.
Am I audible on Zoom?
Yes.
I think the phone setting is first here also. Yes. Can anyone hear me? Jill, can you hear me?
Yes, we can hear see you. The screen is not shared.
Yeah, I'm sharing it again. Guys, can you all see the screen? Is it audible? Like whoever is here. No, I mean last time they said it wasn't visible properly because of light and I don't know.
No, that's early submission, right?
Yeah.
Three weeks.
Yeah. You have a lot of weeks.
Yeah, 29.
You have 3 weeks.
Yeah, 3 weeks. Yeah. Books. I think I can stand.
Start. Jill is here.
Yeah.
Shreya is also. Okay. Hello everyone. So, homework 3 was out yesterday. So, we are giving this boot camp. Please watch the recording later and don't ask doubts which have been already presented here. Try not to. All right. So, as I said, it has already been out. Due date is 1 week from now for early submission. You have to make the mandatory homework 3 part 2 submission. And to get a bonus on part 1, you have to score full points on that. Unlike homework 2, there are no separate MCQs for this. It's a part of the same homework in the handout. And the final deadline is on 29th March. This one would be covering sequence networks. So, Prof has already started GRU, LSTMs, RNNs, and other sequence models in class. So, this one will be based on these 3 networks. Mostly, yeah, actually all 3, GRU, RNN, and LSTMs. More sequence to sequence networks would be covered next week in class, but they are not part of this homework. So like beginning with RNN, as you know, in class and from the recitation we had last week, RNN is basically one block which is applied to every time step in an input which is of the form of one input per time step. Uh, this recurrent kind of block takes in the input at a particular time step and also the computed state or the hidden state of the previous time step. So the main function of the RNN block or RNN cell is to compute this HT or HT minus one, basically the hidden state at any time. And after that, you can of course apply another linear layer on top of the hidden state to give you the output at that cell, at that step. But the main function of the RNN is this much, where you take the input and the previous hidden state. Uh, sorry. Oh yeah, sorry. Yeah. The input and the previous hidden state, you take both of them through an affine combination, which is basically a linear combination, linear layer for both of those things, and then finally feed it into an activation function. Uh, if you do this at time step equals to 0, then you basically need the h of -1, which is normally all zeros. So if your hidden state dimension is say 256, then the initial hidden state would be 256 zeros, a vector of 256 zeros. So you can basically implement this thing, at least the forward with 2 linear layers and an activation function on top of it. Why tanh? Because you have to have a non-linearity, which we studied in the beginning of the course itself, that without a non-linearity, it's essentially a glorified linear combination in the end. So tanh serves as the activation, the non-linearity, and also keeps the output bounded. This prevents exploding gradients, but it leads to vanishing gradients, as you've seen in the last class, and why LSTMs are also necessary. So in this homework, for the first part, you will be implementing the forward and backward of a simple RNN cell, just one RNN cell at one time step. Finally, we would have combination of these RNN cells to give you RNN phoneme classifier. So what this basically means, it's multiple layers of RNNs. Within one layer, the same cell is applied to all time steps, and then you can have multiple such layers on top of each other. And this would be a many-to-one kind of classification task where you have a time series input, which leads to one final output. So as I said, the main function of the RNN is to keep computing these hidden states. And once you've computed all of them, at the very last time step, at the very last layer, you take the hidden state, pass it through another linear layer to give you the final output or the logits, depending on the number of classes there. So the forward for this would be pretty straightforward to implement for you, given you would have already implemented the forward for RNN. For the backward, you would have to think about how you backpropagate through time, which was again taught in the lecture. So you would have to think that how the influences basically flow forward. It's explained in the write-up too. But yeah, you should go through a write-up as well as the lecture to just revise back propagation through time, which you'll essentially be implementing in the backward of this. After this, we'd have GRU. We are not asking you to code an LSTM from scratch here. It's more complex. So we have the simplified version of LSTM, which is the GRU here. This is by far the most time-consuming part, or yeah, actually the most time-consuming part of this homework, mainly because it has a lot of equations which get difficult to implement in backward. So there are principally these four equations. The first two are very similar to each other. So if you get a hang of the first one, you basically have two. So you basically need to kind of implement three equations here. The first one that you see, RT, is basically like the forget gate of an LSTM, which basically controls how much of the previous hidden state you need to retain, because you see that RT is element-wise multiplied to the affine combination of the previous hidden state. So it, in a sense, it functions like the forget gate in an LSTM. Finally, you do have the non-linearity here as well. And the final hidden state for the GRU is basically a linear combination of the previous hidden state and the current hidden states and the current hidden state, or sorry, and the current computation that was NT. The forward for this should be pretty straightforward to implement because it's just a series of matrix multiplications, additions, and then activations. Activations you've already implemented. But for the backward, since it's quite complex, you should break things into its components. For example, if I look at RT, if I have to get the derivative with respect to say XT, I would first get the derivative with respect to RT. Then I would get the derivative with respect to this affine combination inside of the sigmoid. Then I would look at, then basically if I get that derivative, that is basically the derivative with respect to W times XT, right? And after I do that, I can get the derivative with respect to XT. But I have to go through these individual steps to be able to compute that derivative correctly. If I try to directly think of the derivative with respect to XT, it can get particularly confusing. So a simpler example would be, say, if fx is tan h of r element wise wx plus b, then you can basically treat everything inside a parenthesis as an independent variable and start computing derivatives with respect to that. So as I said initially, like if I have to compute the derivative with respect to x, I first compute the derivative with respect to z2 because I know how to backpropagate through tan h. Then I know how to backpropagate through element-wise, because element-wise you just element-wise multiply with the other thing. So that is how I can get the derivative with respect to z1. And once I have the derivative with respect to z1, it is basically like backpropagating through a linear there, right? So you can compute this one as well. So you keep going in these steps and keep applying the chain rule at each one. So there will be two main kinds of backpropagations that you will be doing in this problem in GRU backward. One would be element-wise and one would be matrix multiplication. So let's just quickly revise that. So in element-wise multiplication, if there are two matrices that element-wise multiply to give you a third one, the shape of all three have to be the same. Also, there is no dependence between elements at different positions. So if you see the color coding here, the elements of the same color are dependent on each other. So the element at the same position in A, B, and C is dependent on each other. No other positions contribute to that element of C. So that also means that when you backpropagate, you do not have to worry about any other element when you're thinking about the derivative at any one position. So if you are given the derivative with respect to C, which is DLDC, derivative of loss with respect to C, to get the derivative with respect to A, you can simply element-wise multiply it with B. And to get the derivative with respect to B, you can element-wise multiply this derivative with A. Just look at this color coding again to understand how that flows. whenever you're in doubt with matrix kind of backpropagation, think about it in terms of a single element. Like, what is the derivative with respect to the single element of A, the green element, say, the top left element of A? You'll realize that it contributes to only one element of C, which is the green element in C, and it contributes to that element through one multiplication with the green element in B. So you're only left with one multiplication to get the derivative with respect to that element of A. And you can do this through for all the elements in this matrix. The matrix multiplication case is a little more complex. So let's see, you have three matrices, A and B, which are A cross B and B cross C. They multiply to give you matrix C, which is A cross C. So let's again think of it in terms of one element. Like, if I have to compute the derivative with respect to one element of A, like like Aij. So Aij will basically contribute to all elements in row I of C, and it will contribute to all those elements because it gets multiplied with the jth element in every column of B. So it might seem a little more complicated right now. So look at this diagram, okay? So if Aij, if I take A2, 3, one indexed, it contributes to all elements in the second row of C, and it contributes to those elements because it keeps getting multiplied with the third element in each column of B. So when I'm to back propagate and get the derivative with respect to Aij, I would take the derivatives with respect to C at these positions, multiply them with the respective elements of B, and I'll add all of them together. So in mathematical notation, it would look something like summation of K from 1 to C. So here C is 4, DLDC of uh, each of these positions multiplied by the corresponding element of B. So it's B transpose because you have to now take uh, elements indexed on rows. So, I mean, this is just mathematical notation for you to code it, but please try to understand it with such diagrams. If you do this, you can basically find out what is the derivative with respect to A and what is the derivative with respect to B. And once you have these formulas sorted out, that if A times B is C, then what is DLDA, what is DLDB, you can keep repeating the same formula for every case where there is a matrix multiplication, be it WX, be it WH. Yeah, those are the two kinds of matrix multiplications that you see here. So just try to understand the formula for DLDA and DLDB in the general case when A times B gives you C, and then you can keep repeating this formula and the element-wise formula in this case. So yeah, just try to sort out these back propagation formula before trying to attempt this question. That will make things a lot easier. Once you have the individual GRU created, you will again chain a lot of these GRUs to create another network. Here you do not have to code a backward, you only have to code a forward. What you will be doing here is basically, again, have multiple layers of GRU, and this would be a sorry, this would kind of be a many-to-many problem where at each time step you will be giving one output. So multiple layers of GRU. At the final GRU layer, you have one final hidden state per time step. So you will be feeding that into the same linear layer at each time step to give you the logits at each time step. So in the previous one, you only fed the last time steps hidden state into the linear layer. Here you will be feeding all of them because you need an output at every step. So this is what you'll be implementing for GRU inference. No backward required. Okay, Harni can take over for CPC now.
So the next homework is essentially implementing what is called a CPC. This is something new or something that you haven't heard of. I think next week, Monday and Wednesday, lectures focus specifically on all this today. So the order that you should be doing your homework is go through those lectures, write up bootcamp, and then actually attempt your homework, because those lectures are going to play a huge role in you scoring points in this particular section, and you'll see why. So in any language task like machine translation, for example, where you're converting like one language to another, translating one language to another, there's no 1:1 mapping or no guarantee of it, right? So if you have like 5 words in language A, in language B, you can have 8 words to mean the same thing, or you can have lesser than 5. So there's no 1:1 mapping, which makes training slightly complicated. That's what CTC steps in, where it gives you this whole algorithm to essentially train your recurrent neural network, like your LSTM, to compute weights and to do your backprop. So for all of this, essentially, CTC is what steps in. And even for your homework 3 part 2, which will be covered now right after this, you will hear things like CTC laws, CTC decoding, and all of that. So all of it will ultimately tie in together so that you understand how to train an RNN using this particular concept of CTC laws. So the first thing.
Harini, can you try to talk facing the computer a little because your voice is breaking when you turn the other side.
Okay. Okay. So the first thing that you'll be implementing is called extend target with blank. And as you can see, the task that you'll be implementing here split into 2 steps. The first one is given any sequence, you will be inserting blanks into it. Now, there are reasons why you need to insert blanks, the importance of this particular inserting of blanks, which will become very clear next week during the lecture. But essentially, it helps you during decoding when you want to compress a sequence, which you'll again see in a couple of slides. But pay attention to this particular concept next week during the lectures. So once you have your extended symbols with the blanks in there, you essentially convert that into an integer array, which specifies if there is a connection between any 2 symbols. So on the left, you see that you have blank, B, blank, symbol, and so on. On the right, that array will basically tell you whether between any 2 symbols, you are allowed to skip a connection or not. And the rule is you can skip a connection if the symbols on either side of the symbol that you're considering are the same. So for example, if you look at blank B, you cannot skip. B to blank, you cannot skip. Blank to IY, you can't skip. But if you look at this particular IY, the symbol on either side, are they different? No, which is why it's a 1 here. If this is confusing, it's fine. The write-up has this in a lot more detail. All you need to do is take that algorithm and just code it out, and you'll be able to clear this particular section. Now, once you have the array which tells you how connections move, which is basically you have the structure here, right? You're basically, that array will tell you whether there's a connection that exists between each of those symbols. So you're basically trying to emulate this particular structure in the form of numbers. Once you have this, you have to compute what is known as posterior probabilities. And in order to compute posterior probabilities, you have to compute 2 other probabilities, forward and backward. So let's split each of these and try to understand what each of these actually mean. So when you start decoding, you will essentially start at time step 0 with your first symbol, like whatever you predict at time step 0. A forward probability at a particular time step for a particular symbol basically tells you what is the probability to reach that particular symbol and that time step when you start decoding. So it will take all of the paths that start from the point of decoding up until that particular time step and symbol. Now, in order to implement this, the entire code is present on the lecture slide. So you will have to make some slight adjustments to it in terms of how to slice things, how to access your symbols and all of that. But the algorithm itself will be explained next week and you'll have access to the code as well. Now, the next thing to compute posterior probability called backward probability, which is now I know how to reach, say, IY at time step 3 from the start, but how do I reach the end, which is 8 IY from my current position? That's the probability that backward probability computes. So all the paths that I need to take to move from one particular time step to the end of decode. And this is typically done in a bottom-up fashion. So you'll be starting from the last time step and symbol, and you'll be moving to the current time step and symbol. Again, the lecture slide has all of this code and including how the algorithm works and everything. So you just have to pick that up and figure out how to implement that for this data that we give you and this homework. So finally, when you have forward and backward probabilities, you just multiply the two and divide it by a scaling factor and you get posterior probability. But what that actually means is, given the paths of decoding, what is the probability of that particular symbol is what posterior probability stands for. You know all the paths, you know the probability. of that one symbol at that time step. And why this is important is it ultimately helps you compute. And that's what would essentially be used when you train your network. Yeah, it's the probability of the different paths that would reach that particular time step and symbol when you start decoding or when you have to reach the end. So yeah, so that brings us to the loss, which we'll be giving you the logics. You already have your posterior probability. So again, you just follow this code, which will be available on the lecture slides. And you essentially compute what the loss or the divergence would be, which will be used to train your network. So these are all small parts that tie into your CTC. When you actually use CTC decoding or anything that PyTorch provides, all of this would ultimately be taken care of. The aim of this is for you to understand what happens in each of these steps that will lead to getting the loss out of it. Now, the important part of this homework, apart from GRU, there's another slightly complex part called beam search. So there are two types of decoding techniques. One is greedy search and one is beam search. And these are essentially used to convert your logics into meaningful outputs. If you are giving your input to Google Translate with 5 words and it gives you 0010, wanted to convert to another language. So that's essentially what this decoding would do. As the name suggests, in greedy search, you'll be taking the most probable output at each time step, and then you'll be compressing it using an algorithm, which is again present in the write-up. But to give you a little bit of insight, this is exactly why we need blanks, because it makes your compression algorithm simpler when you have multiple repetitions of a particular symbol. So the algorithm knows whether my final word is going to be BAT or BAAT. And that's where your blanks will play an important role, as you'll see. But the issue with greedy search is you're just taking the most probable output at each time step, and it's not necessary that this is going to be accurate. In fact, you will see that most of the times this might not be that accurate when you try to use GPT and all of that. So that brings us to beam search. And there are two different ways in which you can implement beam search. One way is you pretty much use the code that's going to be given on the slides exactly as is. There'll be very minor changes that you need to make, and then you can run it. But the problem with that is it's not very intuitive, and you don't really understand how beam search works, which is why we introduced efficient beam search in the course, I think a couple of semesters ago. And the way that it works is uh, essentially you start with a blank symbol set. And at each step, you append all of your existing symbol sets to each of the symbols. And you have what is known as a beam width. In this case, it is 3. And you that is determined by K. So you set your K to 3. So if you see K anywhere, that usually means it's beam width. And at every step, you take the top K paths and you keep following this process. So to make it clearer, we initially start with the blank. Uh, let's do this. We initially start with blank and a score of 1. And then you know your symbol set has blank A and B, and that will be your temporary path. Now, in the next step, for each of blank A and B, you would essentially append A blank, A, B, A, C. Similarly for B, similarly for C. And then out of all these, you'll find the top 3 paths because our K was 3, which is why you see in the next step, we only consider these 3 because they had the top 3 probabilities. And then this keeps continuing along for each time step until you get your final path with the maximum score. And this might seem a little complex, but again, I promise it's going to get very clear once the lecture is done and once you actually look at how things are working through the write-up. So you see that at each time step, it sort of looks like a beam is moving, which is how the name beam search comes. And this is going to be a very important aspect of the 3P2 as well. So it'll be really nice if you understand how to do it and then implement it using. But yeah, that brings us to the end of 3P1. We'll be moving to the 3P2 bootcamp now.
Okay, let me share my screen.
Yep.
Okay, so let's start with the homework 3P2 bootcamp. Let's first get into the logistics. So the early submission deadline is March 15th, and that means that you need to reach a 11th stand distance of less than or equal to 12 before this deadline, and also complete your MCQ quiz on Canvas. The final submission for this would be March 29th, after which it'll be considered as a late deadline, a late submission. And there are no other constraints but to not use attention, because one of the major objectives of the upcoming homeworks will be to use attention. So in this homework, we will not allow you to use attention. So we will be getting into a sequence to sequence problem here. And our task over here will be taking these MFCC features. There'll be 27 features, and we will have to do the sequence to sequence task. So let's look at this in more detail. The features over here will be very similar to your homework 1 features, which means that you will have this kind of a sequence of language data. But the difference over here is that you will have phone names, and that the labels will be order synchronous but not time synchronous. Now, what does that mean? So in your homework 1, you had words and you knew which word is going to come after which other word, and that's why you knew the order. And you also knew that at every time step, you get another word. So you also knew the time when you're going to get the next word. But in this case, when you have the phone names, you know the order that the first phoneme is going to come before the next one, but you do not know at which particular time step you're going to get this. And so it is not time synchronous. So that is the difference. And in order to deal with this kind of data, we'll be using CTC laws, which we briefly covered in the first part of this bootcamp and will be covered in the lectures to come. But this is how we will be evaluating your models. And the metric that we'll use is mean Levenstein distance. So this particular metric will also be the one that will be counted on Kaggle. So you will have to reach a mean Levenstein distance of 12 or less. So the less the Levenstein distance, the better performing is your model. So you want to make this distance as less as possible. This is because what we're trying to do here is a sequence to sequence problem. And at the end, what we will be doing is generating a string and then calculating the distance from what could be expected. So you want this particular distance to be as less as possible. So another difference over here in the data would be the length of the sequences. So in homework 1 and 2, we had equal length inputs. But in this homework, you will have variable length inputs. And this does not mean that the number of features in that will be different. It just means that the time duration is different. And so all the features will still be 27 in feature length, but then the start and end time of the duration of the particular element will be different, and so they'll be variable in lengths. So in order to handle this, we'll have to do padding and packing. So let's see what this is. So padding basically just means that you need to add zeros or pad all the sequences with zeros just to match all of them together, the lengths of all of them together. So say you have any feature with X length, you just want all of these particular elements to be the same length in the end. Now, if we think about it, if we just take the whole data set and get the sequence which has the maximum length and try to pad all other input sequences with that particular maximum length, then we would have cases like the one in bottom right, where we are losing a lot of space there, and this would be like very inefficient in the space constraint. So ideally, what we want to do is we want to break up this particular data set into batches and then do this padding. Another thing that we do over here is packing. Now, the reason we do padding over here is that we want sort of rectangular kind of data to enter our model, but a more efficient way of doing it is packing. So you can use padding also, but if you want to use if you want to get like a rectangular input for your models that have like very um, that have a lot of computations like your LSTMs or pyramidal by LSTMs or whatever, you'll need a more efficient way of doing it. And one of the ways of doing that will be packing. This is also something that you need to do in order to prep your data as input for models in the PyTorch. So for example, over here, if we have these elements 0, 1, 2, and 3, all of them are color coded just to make it easier to follow. What we first do is that we first order all of them in a descending way, and this will be with respect to the time steps. So element 2 over here goes from 0 to 6, and which is the highest time duration. And then we go in a decreasing order to element 3, which has only 0 and 1. So we first order them in a decreasing order, and then we order these sequences so that we start from the left to the right, taking one row at a time from each of these elements. So if you can see like the color codes, we go from green, blue, orange, yellow. And in the end, when like the rows get over, we'll just have like repeating rows from the same element. Like in the end, we have two greens. So what this does is it also gives us like a rectangular input, which is now ready to go into any of your sequence models like LSTMs or pyramidal by LSTMs or RNNs or whatever. So this is how you prep your data. So these are some of the important functions that PyTorch already provides for you. The good thing is that everything that I explained over here, you do not really need to code this up. This is already available for you in the PyTorch library. All you need to do is go to the documentation of each of these and figure out how to use them. So here are some of the important things that you will have to use in your homeworks. One thing is that I'm not sure how many of you have tried to experiment with the collate function. So this comes as an argument to the data loader function, and it gives you the flexibility to alter the data for the batches. So if you want to do something to your data when it is getting converted into a batch, you can just write your own custom collate function and then pass it as an argument to the data loader, and that will help you do that. So in this case, we saw that we'll have to pad the sequences or pack the sequences before letting it go through the model. And so we will have to use this collate function argument and do these operations. So pad sequence, as the name suggests, is used to pad all the inputs to an equal length for batching. So this is something you will have to use. Apart from that, what I just explained just before this for packing, you also have pack padded sequence. As the name suggests again, it is used to pack padded sequences. So you'll have to input padded sequences into this function, and it will then give you the packs of the batch of padded sequences. And this will require sequence lengths, because later on we'll have to unpack it. So how the flow basically goes is you need to first pad the sequence, then pack the padded sequence, and then you throw this into your model. The model will then again give you an output, and then you again need to unpack these sequences in order to evaluate it further or put it into the classification layer. So this is how you'll have to go through this. So once you have packed the padded sequence and once you get the output, you'll have to again unpack this. And then this particular unpacking requires the sequence and the sequence length. And so you will have to take care of that also. So this is how like you need to prep the data for taking into your model. And when we now move on to training, we'll have these three parts to it. We'll have an embedding layer, a sequence model, and a classification layer. So we can see this as a proper encoder-decoder module. So encoder over here will constitute of an embedding layer and a sequence model, and decoder, which could be more complex in a lot of other cases, but over here is just a classification layer. So encoder over here is just to sort of get like rich embeddings or rich representation of the data. And so here we use like an embedding layer and a sequence model. And we'll have to then use a classification layer as a decoder. So again, we use encoders as a feature extracting element. And so we might want to use this to generate high level representations of the given input data. But encoders do not generally have labels that are used to train these encoders. So we need to take care of these. And the decoder will then take these feature representations from the encoder and try to generate the closest match of the expected output. And then the output of this decoder goes into your loss function, and then it'll be evaluated or trained further. So embedding layer over here is generally used to increase or decrease the dimensionality of input. Again, this is optional. This is not something that everyone does, but it is highly recommended. And a simple way of doing it is, for example, you have any one statement, for example, deep neural network is great. How we would do this in an embedding layer is just take one word at a time. So deep neural net is given like as an example on the slide over here, say first 3 words. We would just represent each of these words as a one hot vector representation. And what an embedding layer would do is convert this into a continuous representation of real valued vectors. And the shape of this will now be like the embedding dimension that we gave times 1. And so in the embedding output, each of these rows would represent one word. And then when you just do like matrix multiplication with the one hot vector, you could get the value for each of these words. And this could be easy in a lot of cases where you have like word input like we did earlier. But in this particular case, we have like continuous input. Like we do not have words, we have phonemes, and we do not even know when they are coming out, right? So this is continuous representation. And so we cannot use this kind of simple representation for embedding. So what we do in this case is use CNNs, which are known as time delay neural networks. And this can help us in expanding the dimension or increasing it from 27 and make it like larger. So Shreya will now take us through how we can actually do this.
Yes, let me present my screen. Please let me know if it's visible. Is my screen visible?
Yeah.
Yeah. So let us like continuing from what Jeel was explaining. So we are making use of 1D convolutional neural networks in order to perform upsampling of channels from the original 27 to some higher number of features. So here let us consider a simple example wherein we have 3 features and 7 time steps. So we can increase the number of features, like we can increase it to 5 features by using the convolutional neural network. And there can be like different settings of kernel, padding, and stride that we can essentially experiment with in order to increase the number of features. So generally what people do is that they opt for a stride of 1 along with some padding so that it is ensured that the length of the sequence is the same in the embedding layer. So in this way, like only the number of channels or features increases while the time dimensions remain the same. However, like the implementation choice is like completely up to you. Along with this, you can like also have a strided convolution in the embedded layer in order to downsample the time length of the sequence while also increasing the number of features. So again, the choice of stride and padding and kernel size is completely up to you, and it is like completely flexible. So this is what I explained right now. That is like we can make use of strided convolution. And another thing to take care of is that like there's a implementation detail that we need to take note of. So we see that the batches that you get like after padding in the collate function, the batches that you receive would be of the shape B cross T cross 27, where B is the batch size, T is the maximum time length for that particular batch, and 27 would be the number of features. So when you apply 1D CNN, the CNN is expecting the channel dimension to be the first dimension and not the last dimension. But here we see that 27 is the last dimension. So before you make use of the CNN in the embedding layer, you need to make sure that you transpose the first and second dimension such that it is B cross 27 cross T. So after that, you have to transpose it back again before you do the packing and before you pass it on to the sequence model. Because when you are doing, like when you are packing the sequence, it is again expecting the number of channels to be the last dimension. So as we see, like there is like a slight mismatch between what the packing operation is expecting and what this 1D CNN operation is expecting. So you need to take care of the dimensions while performing the necessary transpositions. So this is like an illustration that shows us that we can perform strided convolution in order to decrease the time step. One recommendation is that do not use large strides because that will cause us to lose significant amount of temporal information. Typically, a stride of 1 or 2 is advisable, and do not go for large strides. So when we are another thing to notice that when we are returning something from the batch, we not only get MFCCs and labels, but we also get lengths because every time step is like having a true length. So we are getting these lengths from the collate operation. And in case like you're performing strided convolution, you also need to change the lengths before before passing it through the sequence model. For example, like if you have a batch of size like with a length of 2, 6, 10 and 10, you will not only like get MFCCs, but you will also get a list of these lengths 2, 6, 10 and 10. So like if you apply a convolution that does not change the length of the input in the embedding layer, I think it's like completely fine. But like if you're doing strided convolution, we need to definitely take care of the length as well. And like that would be dependent on the final length of the convolutions output. So like another thing that we can try is like maybe we can try residual blocks, because when we are working with 1D convolution layers in the embedding layer, so people often like tend to use 2 or 3 consecutive layers, or maybe follow a pattern like implement convolution followed by batch normalization and ReLU and something of the similar sort, and then repeat it. Another thing that we can another approach that we can use is that maybe we can add residual connections. This is like similar to the ResNet architecture that we have seen in homework too. This is another aspect that you can experiment with, and yeah, this is something that you can experiment with. So following embedding layer, we can look into the sequence model. Uh, So once you have the embedding layer, you will like ideally have an input of size B cross T cross some higher number of channels, like maybe B cross T cross 64 instead of the original that we saw, which was B cross T cross 27. At this point, like you can, like you're ready to pass it through the sequence model, and what you have at hand is like a padded sequence. So sequence models like LSTMs and RNNs expect packed sequences. So first, what you need to do is that you'll need to pass it through a padded sequence method. You can read the documentation in order to know how to implement this and what correct parameters to provide. Um, and also, irrespective of what you choose, like whether it is an LSTM or GRU or RNN, the basic idea remains the same. The idea is that you pack the padded sequence and then run it through your chosen model. And for this homework, we would like recommend using LSTMs. So another important thing to note is that LSTMs come with their own set of adjustable parameters, and you can experiment with these parameters, like you can experiment with dropout, and then you can adjust the number of LSTM layers, hidden layers, and also you can implement a bidirectional LSTM, which would like essentially result in an output with double the hidden dimensions or the number of channels. So as we recommended for this homework, LSTM is something that we can definitely implement. LSTMs are like the general framework that is expected, but there is like a slight variation of the LSTM, which we called pyramidal bidirectional LSTM. And it is like mostly a simple LSTM, except a pre-step that happens before you actually apply the LSTM. So what we are doing is that we are basically taking adjacent time steps and then we concatenate the channels, so that essentially we are going to double the dimensionality, and also we are downsampling the time length by 2. So you can like definitely go through the documentation for PBLSTM. It is like also included in the appendix of the writer. And yeah, you can check that. We can take one example maybe and see how it works. Suppose if we have an input that consists of 3 channels and 8 time steps, what we are doing essentially is we are taking adjacent time steps, concatenating them, and this would result in a modified input that will consist of 6 channels, as we see, and 4 time steps. And then we are going to feed in this modified input to the by LSTM layer. And for example, if the hidden size we consider is 5, since it's by LSTM, you will get an output which is like twice that of the hidden size. In our case, hidden size is 5, so our output would be like 10 channels. And yeah, so one small implementation detail that you also need to think about or take care of is that what if the input has like odd number of time steps? So in that case, you need to decide what you need to do with the extra time step. So either you can pad the extra time step or you can like remove the last time step. So this implementation is like up to you on how you want to handle this case. And also another thing that you need to think about again is of the lens, because the lens also might get altered since it's packed sequence, maybe you don't really have to do that. But yeah, this is one thing that you have to keep in mind. So we see like the pseudocode which is present over here, it like closely resembles that of a basic BioLSTM, with the only exception is that what we discussed, that one pre-step which is that the original input is reshaped to half the length, and it is twice that of dimensionality. So we basically can implement this with a straightforward reshape operation. And so that was PBLSTM. Maybe next we can go on to the decoder. So decoder in our case is a simple classification layer. And you can use an MLP for classification layer. You have the flexibility to experiment with the architecture. You can adjust the number of layers, activation functions that you're going to use. You can also introduce dropouts in order to mitigate overfitting. So there is no as such strict requirement of how deep the network should be. So feel free to experiment and in order to implement this. And this portion, you must have encountered a similar implementation in homework 1, part 2. And another thing is that maybe you can consider doing sepstral normalization, and also experiment with different weight initializations, and for both convolution and linear layer. And you can also experiment with the scheduler. So we would recommend starting off with reduced LR on plateau scheduler, but another scheduler that you can experiment with maybe is step LR. But for initially you can start with reduce LR on plateau for your experiments. And for optimizer, you can initially start with Adam W or Adam, and you can start using it with, you can start using the learning rate started from a very small value. In order to mitigate overfitting, we can definitely make use of dropout. So you can make use of dropout in all the 3 layers: embedding, sequence, and classification. And it is recommended that you start with a small dropout value and then increase it as the model gets trained. And also you can experiment with using the locked dropouts. Here we have given a reference. You can go through the documentation and try to see how you can incorporate log dropouts and try to experiment with that as well. Another thing that you can maybe implement is time and frequency masking. So again, time and frequency masking can be used to prevent overfitting and improve the generalization when it comes to this homework. So your input MFCCs represent both frequency domain, which is the y-axis, and time domain x-axis. So time masking essentially will involve applying a vertical mask, wherein the frequency masking applies horizontal mask to the MFCCs. So these masking operations are going to ensure that you do not overfit to the training data. So you have 2 options when you are implementing time and frequency masking. So the first option is that you can apply the masking in the collate function, that is when you are returning the batches. In this case, what you do is you mask the data and then you are going to return the masked batches. And another option is that you can directly incorporate the masking logic in your model class, like how you have done in your previous homework, that is homework 1, part 2. So for this homework, you can choose either of the 2 cases, that is implemented in model class or the collate function. And another hyperparameter that we can look at is beam width. So for testing purpose, you can use a higher beam width, but it is recommended that you keep it below 50 for computational purposes. And that is higher beam widths, they demand more computational resources. And you can also experiment with a beam, you can also use a beam width of 1, which is like a greedy search, which also gives good results. However, during validation, using a beam width is not advised, as it can lead to excess computation and wasted time. You can experiment with different values of Beam as well. And final tips would be like to maybe get started with the homework early, as the starter code, as the starter notebook, unlike homework one and homework two, is not as elaborate. You need to code most of it by yourself. So you can start the homework early and reach out to us on Piazza if you have any doubts. All the best. Thank you.
Just a few more things. So, to clarify the collate function and everything that was covered earlier. So, like to understand how that function actually works and how to incorporate padding in that, you can look at the recitation notebook. It has a dummy example, which is much simpler, but you would be using a similar thing. So like LSTMs, etc., can take the simple padded sequence as well. But as GL had explained, it's very computationally inefficient because there are a lot of wasted zeros there. That is why we can pack it and then send to the LSTM. But for all other things like the CNN, etc., and even the MLP at the end, you need the padded sequence. That is why we pad it first. And only for the LSTM do we pack it. And then we unpack it again. Like we pad it and then we feed it to every other thing. The second thing is that, so Shreya was talking about the fact that you can have strided convolutions before LSTM, and then you can also have PB LSTMs, which further do downsampling. So please be aware of how much downsampling you're doing eventually. Like sometimes people have like 2 or 3 strided convolutions, which basically means downsampling by a factor of 4. And then they have 4 more PB LSTMs, which means downsampling by a factor of 32 or 64 eventually, which basically means that the sequence to the last, that the final sequence is so small, there's so few time steps that when you apply the loss function, there is just not enough information to actually compute the loss. And the loss that you're using, that is CTC loss, it gives you NaN values. So even if you look at the CTC loss documentation in PyTorch, it says that it can give you NaN if the number of input time steps is too small. So please be aware of how much downsampling you're doing. Be mindful of that. And the other thing is about the time masking and frequency masking. So if you look at the documentation on how PyTorch implements that, the input to that is frequency cross time. So it's batch cross frequency cross time. But in your case, batches are always batch cross time cross frequency. So if you apply time masking to that thing, it will behave like frequency masking. And if you apply frequency masking, it will behave like time masking. So please be aware that if you apply that either in the data loader or in the model, you need to do you need to permute your data before and after the masking. Just like you have to do some permute before and after conf layers, right? So please be aware of those things. Any other doubt? Yeah. No. So the padded sequence, padding is to create those rectangular batches, right? So if you have 4 elements in a batch, everyone has different number of time steps. You cannot make that into a batch. So you pad it so that you can pass it through a convolution layers and everything. But after that, when you feed it to the LSTM, you pack it. Shreya, can you just go back to the packing slide if possible? Also, wait, I can show you. Yeah. So in the packing thing, you don't have the extra zeros. In the packing thing, you basically arrange every time step of every element one by one till you exhaust all of them. And the LSTM is optimized to deal with that kind of a sequence. So you do not have the padded things in there. PyTorch, you have to pass the lengths of the individual things, individual data items in the batch as well, so that it knows that at what point should it cut it off and pack it. And similarly, when you want to convert it back to a padded sequence, you again have to pass the lengths, or it stores it, so that all that information regarding lengths is retained before and after the packing. For the encoder as well as the final decoder, which is the MLP. You can use the padded sequence even for LSTMs, but it is very computationally inefficient. No, only LSTMs, etc. The sequence models, they are able to take a packed sequence. Yeah. Again, just look at the recitation notebook. It has examples of how to just feed padded sequence into a sequence model as well. But you can compare on how it performs versus a packed sequence. Anything else? No?